In Chapter 21, we will be looking at carboxylic acids and their derivatives. You can see a picture here of two thermometers, one where presumably there's a person with a fever, and one where a person has taken aspirin and that fever has been lowered. We will take a look at aspirin and penicillin and other drugs that may have carboxylic acids or derivatives in their structure. Here are several different carboxylic acids as well as derivatives of them. The most common and simple one is acetic acid, which is responsible for that smell of vinegar. The U.S. produces over 2.5 million tons of acetic acid every year, and most of this acetic acid is actually used to make vinyl acetate. Vinyl acetate is used in paints and adhesives. We can see butanoic acid, which is responsible for the rancid odor of sour butter. Hexanoic acid is what you may smell if you have dirty socks sitting in the corner of your dorm rooms. Lactic acid is the smell for sour milk. The structure of aspirin is shown there, which is what we synthesized last semester. We also have aminosalicylic acid, which is used in the treatment of tuberculosis, and isotretinoin, which is used in the treatment of acne. Carboxylic acids and derivatives play a large role in everyday life. When we name monocarboxylic acid, it's named with the suffix oic acid. So we use the longest carbon chain as the parent name. This one has 4 carbons. This becomes butane or butanoic acid. The carboxylic acid will always be carbon 1. If you have other substituents on there, we just name those as substituents. This is 5-hydroxy 4,4-dimethyl pentanoic acid. The common name for this one is formic acid. It can also be called methanoic acid. Acetic acid is the common one here, or ethanoic acid. This can be called propanoic acid, or sometimes is propionic. The common name for this one is butyric acid, or the butanoic acid from over here, and this one is benzoic acid. If you have a dicarboxylic acid, that's named with the suffix dioic acid. So this one here with 5 carbons would be pentane dioic acid. There's also other common names for dicarboxylic acids. There's oxalic acid, malonic acid, succinic acid, and glutaric acid. And you won't have to worry about memorizing those. Carboxylic acids have trigonoplanar geometry because it contains that sp2 carbon. It also has strong hydrogen bonding between the acid pairs. You can see 2 carboxylic acids here that can hydrogen bond to each other. So the OH of one can hydrogen bond to the carbonyl oxygen of another, and vice versa. This is why when we're looking at IR spectra, we can see the huge ugly peak where we would expect an OH stretch. Because of the hydrogen bonding, carboxylic acids have high boiling points. For acetic acid, the boiling point is 118 degrees Celsius versus something with similar mass. 2-propanol or isopropanol is 82 degrees. This is benzoic acid, which we've seen previously. If you have a carboxylate ion of that, we name this with an O8 ending. So we name the cation ion first. This would be sodium. And instead of being benzoic acid, we drop the ic acid and use O8, sodium benzoate. Compounds that end in the suffix O8 are often found in food ingredients listed as preservatives. If you look at your food labels, you may see sodium benzoate appear in your ingredients list. And oftentimes sodium hydroxide is the strong base that's capable of reacting with 100% of the carboxylic acids. When a carboxylic acid is added to water, the equilibrium generally favors the acid. So in a mixture of acetic acid and water, it's going to favor this. Our pKa of the carboxylic acid is around 5. And for H3O+, this is in the negatives, which is why the equilibrium favors the acetic acid. The pKa of benzoic acid is 4.19, and that's going to be more acidic than acetic acid because now that has resonance. For this one, a regular acetic acid is 4.76. If you add an ethyl group here, this is 4.87. If you recall, HCl is -7. This is 4.76, and then a regular alcohol is around 16. When we add electron withdrawing groups to there, that's going to make it more acidic. So 1 chlorine on that carboxylic acid will make this 2.9. 2 chlorines is 1.3. We add 3 chlorines onto there, and that's 0.9. And then proximity will also play into that. This is 4.1. When it's 2 carbons away, 3 carbons away is 4.5. With benzoic acid, if you have a group that is para, the electron withdrawing group that is strong lowers the pKa to 3.4. An aldehyde, which is not as strong of a withdrawing group, is 3.8. Chlorine is 4. Just regular benzoic acid is 4.2. If you have a methyl group para, that's 4.3, and then an alcohol is 4.5. So we have different methods for preparing carboxylic acids that we've already seen. The first from chapter 9 is oxidative cleavage of an alkyne, where we cut this in half, we do ozonolysis followed by a water workup, and that makes 2 carboxylic acids. We can also oxidize a primary alcohol using the Jones reagent to get a carboxylic acid, or we can do oxidation of a benzyl proton to get benzoic acid. One other reaction that we can do is to hydrolyze a nitrile using acid and heat, and that will give us the carboxylic acid here. And the way that we can make a nitrile is to do an SN2 reaction using NaCN. This gives us the nitrile. We then add acid plus heat. So here we've added a carbon as well as made it into a carboxylic acid. Another reaction that we can do is to react a Grignard with carbon dioxide. So that will attack here. And we get the carboxylic acid. So if I do that, attack here, one of these electrons goes up. We follow that with H3O+. That's going to grab a proton. And you get that carboxylic acid. So if you remember how to make a Grignard, you have an alkyl halide. We add magnesium. And then to this, we would add CO2. This is the carbon that gets added. So CO2 followed by acid. Once we've made a carboxylic acid, we've seen a couple ways to do that now. The reactions that we can do with them, some of these we've already seen. The first is using lithium aluminum hydride in excess. And this will get you the alcohol. So when you're doing this reaction, this aluminum hydride is our source of H-. So one of these H's with the electron is going to pull off a proton to give us the carboxylate. This is plus AlH3. And then one of these H's can now attack this carbonyl, and these electrons are going to form a bond with aluminum. We have AlH2, the hydrogen that was added. This is a leaving group, so that can leave. These electrons are going to go down to form that carbonyl, and this gets kicked off. And then we get the aldehyde. And there's more lithium aluminum hydride present. One of these H- can attack here. We have acid present. and then we get the alcohol. And that's a primary alcohol. Another reaction that we can use is a mild Borane reagent, which we saw previously to do an anti-Markovnikov alcohol addition across an alkene. We can use that same BH3 to reduce a carboxylic acid. If you had a ketone present with a carboxylic acid, the BH3 will only reduce the carboxylic acid. Now when we're looking at the different derivatives of carboxylic acids, the first one is the acid halide. If you have an oxygen between two carbonyls, this is an acid anhydride. You've seen the ester before, and if you have a carbonyl with an NH2, this is an amide. This is a nitrile. Acid halides and acid anhydrides are pretty unstable, so they're not very common in nature. And esters that you may have encountered are in different perfumes or scents or fruit-flavored things include methylbutanoate, which is the smell for pineapple. Isopentyl acetate is the banana smell, and butyl acetate is the pear smell. Amides we'll see very common in nature in amino acids, which is the makeup of our DNA. So two amino acids combine together to make what is called a peptide bond, which is the same thing as an amide bond. The structure of proteins in our bodies are connected by amide bonds, which are these carbon double bond ends to another amino acid. There's lots of amides in pharmaceuticals. Melatonin contains an amide. Solipidem or Ambien, which is the sleeping medication, that contains the amide functional group there. Sonata, which is another sleeping medication, also contains that amide functional group. These have similar rings as well, or similar structures. There's just a couple variations there. The three drugs that you see over here, diazepam, lorazepam, and temazepam, these are all anti-anxiety medications which also contain that amide functional group. These structures are also similar to each other. Acid chlorides are named similarly to the carboxylic acid. Acetic acid, if you swap it out with a bromine, becomes acetyl bromide. Benzoic acid becomes benzoyl chloride. For naming amides, you have acetic acid. That one becomes acetamide. Benzoic acid becomes benzamide. And when you name anhydrides, it's just this part of it, which is acetic, benzoic, which is the other side, and then anhydride. So acetic anhydrides, if they have the same groups on both sides, you just replace the acid with anhydride. And if it's asymmetric, which is the case here, you list it alphabetically, adding the word anhydride. These are the same parts, which is the acetic part. This would be acetic anhydride. Esters are named by naming the alkyl group that's attached to the oxygen first, followed by the carboxylic acid's name with the suffix -ate. This one here on the other side of the oxygen in green is an ethyl group. And then this is the acetic acid. So this becomes ethyl. So you drop the ic acid and end it in -ate. So this is acetate. Or ethyl ethanoate. This group off of the oxygen is isopropyl. This would be 2-methyl butanoate. So this is kind of named like the carboxylic acid salts. We have that -ate ending. If you have a common name like the acetic acid, then you would use the -ate ending. But for regular alkyl carbon chains, we use the -ate. This one is ethyl benzoate. And this one here, the phenyl group is on the oxygen, so this is a phenyl. This becomes phenyl acetate or phenylethanoate. So we named these earlier. This is the acetamide, benzamide. Other amides are named by replacing the suffix ic or oic acid with amide. If the nitrogen atom of the amide group has alkyl substituents, they're placed at the beginning of the name with N as the locant. So for example, this would be an amide. There's a methyl group on here, so this would be N-methyl, and then acetamide. This has two methyls on the end, so this would be N-N, dimethyl, acetamide. So we kind of treat the groups like them being on a nitrogen instead of being on a numbered carbon. If you have a nitrile, this is acetonitrile. So nitriles, we just drop the ic or oic acid ending and then you replace it with O-nitrile. So this one is benzonitrile. The most common reaction that we're going to see with carboxylic acid derivatives is the nucleophilic acyl substitution. And this reactivity can be affected by induction, in resonance, sterics, and the quality of the leaving group. So we can see that the most reactive carboxylic acid derivative is the acyl halide. This has a good leaving group versus the amide, which is a bad leaving group. So these two are the most reactive, the acid chloride and the acid anhydride. And if you remember from the beginning of the chapter, we talked about these two being unstable and not being very common in nature, and that's because they are very reactive. So this is the order of increasing reactivity. So when we're looking at nucleophilic acyl substitution, we have different carbonyls that can react. When we looked at aldehydes and ketones, when we added nucleophiles, these generally produced alcohols. But with something with a leaving group here, we're going to see a different product. So if you have an acid chloride derivative where Z is a leaving group, you react it with a negative nucleophile. Those electrons will come up. And then here we have Z, which is the leaving group. If the carbonyl can reform and then kick off a leaving group, it's going to do that. So then we form a carbonyl. In the case of ketone and aldehyde, there wouldn't be a leaving group here, that would just get protonated. So the acid chloride is the most reactive of the derivatives. When we're drawing the mechanism for this, you want to make sure that you show all of the steps and not just draw it as an SN2 mechanism. So this is our nucleophile, this is our electrophile. This attacks here, the electrons go up. We have the OMe that attacked, and then we have a minus charge here. These electrons can then come back down and kick off the chlorine. And now you form the ester. So this is the tetrahedral intermediate. And then from there we have the formation of the carbonyl. So what you don't want to do with the mechanism is to make it look like an SN2 reaction, where this goes up, this comes up, that goes back down and kicks that off. We should not be showing it all in one step. And if you notice in the mechanism here, we started with the negative nucleophile, our charge was negative, and then it went to neutral, but we're not mixing negatives and positives back and forth. If we react an ester with water and a carboxylic acid, with water and an acid, we're going to get a carboxylic acid plus the ROH. And this is under acidic conditions, so we're going to see a proton transfer. And then water will act as our nucleophile. If we want the OR to leave, so we're going to do a proton transfer. These electrons will come down to kick that off. And then there's a proton transfer in the last step. So we can see the reaction coordinate here. The first step was the proton transfer, which makes the carbonyl much more electrophilic. So we get this proton transfer first, which makes a very good electrophile for the nucleophile to attack. If the water had tried to attack the ester as it is, you would see there's a very large energy to overcome. And also then we have these two different charges here. This is not very stable and high in energy, which is why we protonate first to make it a better nucleophile. If we add OH minus to the ester, the activation energy is much less, so this reaction will proceed without needing to have it protonated by the acid. So this is a strong nucleophile, whereas water was a weak nucleophile. And that's why we had to protonate it first also. So strong nucleophile with the electrophile here, that's just going to attack straight out the door. To give us the carboxylic acid. Neutral nucleophiles are generally less reactive, but they can still react if there's enough time for it to do so. So you could make an amide from an ester. It just takes a really long time. And now we have these charges. But a couple steps later, you'll end up with the amide. So here's a couple of practice problems for you. If we have an acid chloride reacted with water, water is the nucleophile, so we'll get a carboxylic acid. Sodium hydroxides are a strong nucleophile. We'll get a carboxylic acid. An ester with acid will give us a carboxylic acid as well.